So far in this unit, we have found relative or local extreme values, so relative mins and maxes or local mins and maxes. But today we're going to work on finding absolute extreme values, and we're going to learn one more existence theorem called the extreme value theorem. So an absolute or global maximum or an absolute or global minimum are values of f, so they're outputs, and those are going to be values that are greater than or less than, well, all of the other values for the function or on a closed interval. So if we look at a couple quick examples out to the side, let's say that I have the function, or let's say that I have the function f of x is x minus 3 cubed plus 1. Nope, not cubed. I'm so sorry, squared. All right, so if I remember from algebra, this is a parabola that would have a vertex at 3, 1, and it's a concave up parabola. All right, so this function f is continuous everywhere. It has a domain of all real numbers, and I could say that this function f has an absolute minimum value of 1. So it has an absolute minimum value of 1 at x equals 3. So where x equals 3 is the location. So I can see that this value will never get, or this function f will never get lower than 1. And I could also see that on both sides of f, that f is increasing forever. So this function does not have an absolute maximum value. Now, this is looking at f on the interval of all real numbers. Usually, we look for an absolute min or max on a closed interval, but a function such as a quadratic or an absolute value function that has a vertex that's a relative min or max can have an absolute min or max across its domain. One more example. Let's say we just, that's not horizontal. Let's say we consider maybe we have a fourth degree polynomial function. If I look at this function, it's going to have a I don't know how that turned into a heart. Sometimes OneNote does some funny stuff to me. All right, this function is going to have a relative max here and a relative maximum value here. This function also has a relative minimum value. So if I asked you if it had an absolute min or max across its entire domain, we could say that this particular value, this output, is our absolute or global max, because this function is going to continue to get lesser and lesser values of y on the left and the right, but it will never have a value greater than the value at that maximum value. So notice in both of these examples, our absolute min or our absolute max were at critical values of the function. So in that top example, that was where f prime of x was equal to 0. And then same in this next example, at our 3 relative extreme values, f prime of x was also equal to 0. And remember, we want to look for where f prime of x is equal to 0 or undefined. So we have a couple of examples of finding absolute mins and maxes on an open interval. But when we look at this theorem, the extreme value theorem tells us that, first of all, if f is a continuous function, or rather, if f is continuous on this closed interval from a to b, so f has to be continuous on this closed interval, then f has an absolute maximum and minimum value on this interval. So if you notice before, on these open intervals, we said this function maybe only had a min or a max, but if I were to close this off and I were to look like from some a value to some b value, now this function does have an absolute max on that closed interval. So one of our takeaways is that the absolute min or max can occur at a critical value or at the endpoint of an interval. And that's going to be a big idea. So an absolute min or max can occur at a critical value. So again, we want to look for where f prime is 0 or undefined, or at x equals a or b, where a and b are the endpoints of the interval. So let's look at these 4 examples below. Well, one example, 4 images. Each figure below shows a function defined on the closed interval from 0 to 6. We are asked to determine whether there exists a maximum and or minimum value for each figure. So notice in the first example that from 0 to 6, this function is not continuous on that closed interval. In fact, this function has a vertical asymptote at x equals 3. So that does not necessarily mean that we cannot have an absolute min or a max. It just means that the extreme value theorem cannot guarantee the min or the max, because this statement, f is continuous on the closed interval from a to b, that statement must be true to be able to guarantee the absolute min or max. So if we look for this function, we start at some value here between 0 and -2. And if I trace this graph, I can see that at this side of the asymptote, it's going to go down forever and ever and ever. So because of that, I have no minimum value there. So there is no minimum value, because as that function approaches that vertical asymptote, or approaches 3 from the left, the function value is going to decrease indefinitely. So on the right-hand side, I notice a similar thing happen, that as we get closer and closer to that asymptote from the right, that this function is approaching positive infinity, meaning that the function is going to continue going up forever. So there is no maximum value either. So this particular example, we have no minimum and no maximum. In the next example, notice that we do have a jump discontinuity at x equals 3. So again, this function is not continuous on this closed interval from 0 to 6. But that doesn't mean that the function couldn't have a min or a max. So on the left-hand piece, if I start at where y is equal to 0, at x equals 0, as I trace this function, notice I'm going to get really, really, really close to 10, but this function value is never actually going to be 10. And in fact, it's going to get closer and closer and closer. So let's say that we think maybe the function value is where y equals like 9.99999. Well, guess what? We could add another 9 to that, and now we've gotten closer to 10 without being 10. The one thing we cannot say is we cannot say that function value is 9.9 repeating. That by definition is the number 10. So this function, if I think of this y value as a finite value, I could just keep adding a 9 on it, and I can keep getting closer and closer to 10 without ever actually getting to 10. So this function has no maximum value. As I look at the second piece of the function, though, as I start where x equals 3, at y equals 6, and kind of trace downward, when x is equal to 6, the function value is -6. That is a minimum value. There is no other value of this function on the interval from 0 to 6 that is less than -6. So this function has a minimum value of -6. So that's our y value. And this happens at the location x equals 6. All right, in the third figure, again, we have another example where a function is not continuous from 0 to 6, but we do have a maximum value. So again, from the left, I could trace this function And I noticed that like as I'm using this piece, as I'm approaching 3 from the left, I'm getting really, really close to some number that's between 6 and 8. Maybe it's 7. As I get really, really close there, I'm never going to actually achieve the number where that open circle is, that value, but my function value at 3 is 10. So this function does have a maximum value of 10. So that's an output, like a y value, y equals 10. And again, this occurs at or when x is equal to 3. Now this function also has a minimum value because on the right-hand piece, again, if I trace this until x is equal to 6, this function is defined at x equals 6 and its output is negative 8. And on that domain from 0 to 6, there is no time where this function achieves a lesser value or a value lower than negative 8. So we do have a minimum value of negative 8. And again, that's going to occur at x equals 6. So sometimes I think of x equals 6 as the location of the minimum, where on the x-axis it occurs. The minimum itself is the y value. It's an output. All right, on this very last example, I notice that even though this function is not continuous at 0 and at 6, the function is otherwise defined on that interval. So again, this function is not going to have a maximum value. Whoops, I've got too many things going on. This function is not going to have a maximum value. As I approach 6, same as before, I'm going to get really, really, really close to 10, but never equal 10. So this function has no maximum. However, it does have a minimum when x is equal to 2. Its output is negative 6. So the minimum value is negative 6, and that occurs at x equals 2. All right, so just to be clear, again, just because a function is not continuous on the closed interval a to b, it doesn't mean that it cannot attain an absolute min or a maximum value, but the extreme value theorem guarantees us for all continuous functions that they must attain an absolute max or minimum value. And again, this is a little bit redundant, but we said in those figures that the absolute min or max must always occur at a critical value. So again, a critical value is where our derivative is 0 or our derivative does not exist, it's non-existent, or at an endpoint of the interval. So if I'm looking at the closed interval from a to b at either x equals a or x equals b, that's where our mins and maxes will always occur. Okay, so in this first example, we are asked to find the absolute maximum and minimum values of f on the closed interval from -2 to 4. So I want to point out that we're finding the maximum, the absolute maximum and minimum values. So again, those are outputs. Those are y values. We know that we're looking for them for values of x between and including -2 to 4. So the first thing we want to do, similar to when we're finding relative mins and maxes, is we first want to find our derivative. So f prime of x, I should get, let's see, x squared minus 4x minus 5. And again, I know that this derivative is never undefined. It doesn't have a denominator. So I want to know where this derivative is equal to 0. And I, of course, want to factor and apply the zero product property. So I would get x equals -1 and x equals 5. But remember, I'm only looking for an absolute min and max on this interval from -2 to +4. So x equals 5 is not going to be on that interval. So when we find relative min and max values, we can use a number line test because we're only considering critical values as like possible candidates for locations for relative extrema. But when we are finding absolute mins and maxes, we really need to compare the function values. So I'm going to strongly suggest that we make a table, and in our table, we're going to include the endpoints of our interval and any critical values between them. So in my table, this is not a table of x and f prime, but this is going to be a table that we use to just organize the actual function values we're looking for. So we said our endpoints of the interval are -2 and 4, and we also want to include the critical value between those, -1. And even though 5 is a critical value, we're not including it in our table because it's greater than 4. So we're going to evaluate these three values. I do want to back up though. When we are doing our work, when we are answering this as a free response question, we really actually need to make really clear to the reader that we know the extreme value theorem and we don't need to cite it. But there's a sentence that I'm going to encourage us to write, and I usually write it at the beginning, but I kind of forgot. I just got excited about jumping into this problem. I get excited about taking derivatives sometimes. So what I'm going to encourage us to say here is really what we know from the extreme value theorem is that the absolute maximum and minimum, so I'm going to write max/min, values of f can occur at critical values, and in this case, that's where f prime equals 0, or at endpoints. So the reason I really want us to be in the habit of writing this is that AP is a little picky about us showing what we know, and when we make this statement, it's really proving that we know that we can apply the extreme value theorem here. And that is often going to make our argument a little bit stronger. And it shows the reader why we're making this table. Like, why else would I look for f of -2, f of -1, and f of 4? Well, it's because I'm looking at endpoints of my interval and at my critical value that's in between them. Okay, so out to the side, I'm going to evaluate those three, values. Evaluate the values. F of -2, let's see, that's 1/3 times -2 cubed, so -8/3, minus 2 times -2 squared, so that becomes -8, and then minus 5 times -2 is a plus 10 there. So let's see, we get -8/3, I'm going to get a common denominator, minus 24/3 plus 30/3, that's like -8 plus 6/3, which is -2/3 there. So we do need to be able to do that kind of calculation to put that in our table. When we go to find f of -1, that one might be a little bit easier. So 1/3 -1 cubed is just -1/3. Minus 2 times -1 squared is -2. Minus 5 times -1 is plus 5. So that's the same as -1/3 plus 3, or 3 minus 1/3, or 9/3 minus 1/3, which is 8/3. Finally, when we go to find f of 4, and this is a non-calculator problem, so we need to be able to do this without a calculator. I notice that I'm like each of my terms in f has a factor of x, which we're plugging in the 4 for. So I might do myself a favor in a moment and factor that out. So I'm going to think of this as like 4 cubed over 3 minus 2 times 4 squared minus 5 times 4. And to get out of doing 4 cubed, not that it's the end of the world and you can't do that math. If I factor a 4 out of everything, I mean, like, you could do this problem any way you want, but I like to use factoring to my advantage. So I'm pulling a factor of 4 out of all 3 of those terms on the outside. That way I could just multiply by 4 at the end. So I have 4 times 16/3 minus 8 minus 5. Negative 8 and negative 5 combined is what? Negative 13. And 13 thirds would be like minus 30, or sorry, 13 with the denominator of 3 would be like negative 39 thirds. That's what I was trying to say. So 16 minus 39 is what? Negative 23. So we get 4 times negative 23 thirds, and that is negative 92 thirds. Now, if you don't like how I factored out that 4, by all means, do it a different way. But we need to be able to get an answer like negative 92 thirds without using a calculator. So finally, we still haven't answered the question yet. We were asked to find the absolute max and minimum values. And in our table, we can see them now, right? I know that negative 92 thirds, that is going to be our minimum value. That is the least value in our table. That is less than negative 2 thirds for sure, by a lot. The other number in my table that's my maximum is positive 8 thirds. And it's the only positive value, so that one's maybe a little easier to think about. So when I go to answer the question, when I'm finding the minimum and maximum values, it doesn't hurt to include the location. It's not mandatory if we're not asked for the location, but it's better sometimes to give too much information than not enough. I'm going to cheat and write my answer in no man's land since I did so much work finding f of 4. And I'm going to say the maximum value of f, and really I should be specific and say on the closed interval negative 2 to 4 is 8 thirds. So 8 thirds is the maximum. But I might say that this occurs at x equals negative 1. So it doesn't hurt to give the location of the maximum. And furthermore, the minimum value of f on the interval negative 2 to 4 is negative 92 thirds. And again, this occurs at x equals 4. All right, so if we look at the next example, we are asked to find the location of the absolute extrema of G. So when we're asked to find the location, those are really just x values. Now, if we do end up finding the location and the value, that's fine. It's okay to give like more to our answer as long as what we give is correct. We just want to make sure that we answer the question completely. So again, what I should have modeled before is that if this is a free response style question, I want to explain to the reader like why I'm about to do the thing that I'm about to do. So I might write that the absolute, you could use the word extrema to be general, or extreme values. I'm going to say extrema. The absolute extrema of G, so again, that's like the absolute max and mins, can occur at critical values or at endpoints. And again, our critical values will be where G prime is 0 or undefined. And our endpoints are going to be at x equals negative 2 and 1 for this problem. All right, so we know the next thing that we need to do is to find our critical values because we already know our endpoints. So we need to find our derivative. So using the product rule, I should get 2x e to the x plus x squared e to the x. And I know I'm setting this derivative equal to 0. I also know that it's never undefined. So I'm going to go ahead and factor out a GCF of x e to the x. So again, this is g prime of x. And that's what I'm going to set equal to 0. All right, so using the zero product property, I have 3 factors. I have the factor of x, so x could be 0. I have the factor of e to the x, so that could be 0. And then I have the factor of 2 plus x. And the zero product property just tells me where my zeros could occur. Well, x equals 0, that's definitely a 0, but I know that e to the x cannot equal 0. So that factor will not be 0. And if 2 plus x equals 0, that happens when x equals -2. So we get two critical values of g, and notice one of them, -2, is also an endpoint of our interval. And that's fine. Okay, so now, again, we said the next thing we really want to do here is to make a table of values. We're not using a number line because we have to compare the values to g of -2 and g of 1. So again, when we make a table, it's critical that we label our table. In fact, without these labels, I won't have any idea what this is. I want to include -2 and 1, my endpoints. And we said the critical value in between them is 0. So out to the side, when I evaluate g of -2 rather, again, I'm going back to my function g. This is not g prime. I get -2 squared times e to the -2 power, which is 4 over e squared. All right, for g of 0, well, that's just 0 times 1, 0 times e to the power of 0. That one was easy. And then lastly, for g of 1, I just get 1 squared times e to the 1, which is just e. Okay, so that one wasn't so hard. So now when I'm looking at these values, and again, answering the question, I'm finding the location of the absolute extrema. I still need to be able to reason about like 4 divided by e squared as compared to e. So as I look at these three values, 4 divided by e squared is a positive number. E is a positive number. It's between 2 and 3, closer to 3 than it is to 2. And 0 is just 0. So I could look at this and I know that 0 is the minimum value. So the question is, which is greater, e, which is approximately 2.7 and some change, or 4 divided by e squared? And so if I remember that e is less than 3 but greater than 2, if I think about e squared, that's going to be less than 3 squared, so less than 9, but greater than 2 squared, so greater than 4. So that means that 4 divided by e squared is going to be less than 4 divided by 9. Wait a minute. Sorry. It's going to be greater than 4 divided by 9. I was thinking about this is like what we think about when we're considering reciprocals, when we take the reciprocal of an inequality that we have to flip it. So this is going to be between 4 divided by 4, which is 1, and 4 divided by 9. So since we're like dividing a number by those three denominators, it's like we're multiplying by reciprocal. So I do have to flip those inequalities. I'm just laughing because I just finished earlier filming that the lesson on monotonicity where we talk about that. So, okay, so all that to say, we know that 4 over e squared is definitely less than 1, which means it's definitely less than e, which means that e is our max. So we don't necessarily have to show that work or that thinking out to the side. We just have to know for sure that e is greater than 4 divided by e squared. All right, so going back to the question, in fact, I'm just, for space, I'm going to erase this. I always wonder, is that really frustrating when I write stuff down? Maybe you're copying it down and then I go back and erase it. So I'm sorry if it is. You can always keep it. You don't have to erase it. Okay, going back to the question, what's the location? So it is better to give too much correct information here than not enough. Caveat on it being correct. This is really just asking for the locations, so the 0 and the 1 for the min and the max. But just to be certain, I might just answer the whole question and say what the min and max is. So we could say like the minimum or the absolute minimum. I abbreviate a lot. The absolute minimum value of G on the interval, closed interval from -2 to 1 is 0 at x equals 0. So like that's the important part. Otherwise, we could just say the minimum value occurs at x equals 0. And then the absolute maximum value of G on the interval -2 to 1 is E at x equals 1. So again, if I don't include the information about the E, I could at least say that the absolute maximum value occurs at x equals 1.